Welcome to the session on sequences and series, geometric series. The objectives for this session are to prove the formula for the sum of a finite geometric series and apply it. Let's remind ourselves of geometric sequences. The formula for the nth term of a geometric sequence is u subscript n equals a times r to the power n minus 1. Here, u subscript n is the nth term, a is the first term, and r is the common ratio. Let's take a look at an example. An increasing geometric sequence takes the form, or could take the form, 3, 12, 48, and 192. 3 has been multiplied by 4 to give 12. 12 has again been multiplied by 4 to give 48, and 48 has been multiplied by 4 again to give 192. All the values have been multiplied by the same constant in order to give the next term in the sequence. And now for geometric series. A geometric series is the sum of the terms of a geometric sequence. So, for example, a geometric series could take the form 3 plus 12 plus 48 plus 192. We've simply added the terms of the last sequence. The notation we use is s subscript n. This denotes the sum of the first n terms of a series. So in this example, we have that s subscript 4 equals 3 plus 12 plus 48 plus 192, which equals 255. Now let's take a look at another example. We are required to find the sum, or the formula for the sum, of the first n terms of a geometric series. The sum of the first n terms of a geometric series is going to take the form s subscript n equals a plus ar plus ar squared plus ar cubed plus all the way up to plus ar to the power n minus 2 plus ar to the power n minus 1. We can multiply this by r, and notice how all the terms now shift, and they are very similar to the terms in s subscript n. If we subtract the second series from the first series, we obtain s subscript n minus r times s subscript n equals a minus 0, which is a, and then we add to that ar minus ar, which is of course 0. And similarly, ar squared minus ar squared is 0 again, and this continues until almost the end of the series, until we get to the last term of rs subscript n, where we apply 0 minus ar to the power n to obtain minus ar to the power n. We can tidy this up, as shown here, to obtain s subscript n minus r times s subscript n equals a minus ar to the power n. We can now rearrange or factorize as shown. And then divide by 1 minus r, as shown here, and of course r does not equal 1, otherwise this would not be valid. And this of course also equals a times r to the power n minus 1 all over r minus 1, for r not equal to 1. So we have the formula for the sum of a geometric series. Now let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. We are required to consider the geometric series 2 minus 6 plus 18 minus 54 plus 162 plus and so on, and then find its sum for the first 10 terms. We can clearly see that the value of a, or the first term, is equal to 2 here, and the value of the common ratio r is equal to minus 6 over 2, which is equal to minus 3. We also have that the value of n is equal to 10, because we're considering the first 10 terms. And so we can substitute these values into the formula for s subscript n to give us the sum of the first 10 terms. So here's a equals 2, here's r equals minus 3, and here's n equals 10. And this gives us minus 29,524. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So here we're required to consider the geometric series 2 plus 6 plus 18 plus 54 plus 162 plus and so on. We are required to find the least number of terms required for the sum to exceed 1000. So let's solve this. We have that the first term a is equal to 2, and the common ratio r is equal to 6 over 2. We've divided the second term by the first term. And this of course gives us 3, so r equals 3. We are given that the series is greater than 1000. So let's let s subscript n equal 1000, and then substitute all these values that we have in the formula for s subscript n. So 1000 goes here, the value a equals 2 goes here, the value of r equals 3 goes here and here. And of course, n is unknown. We're going to try and find n in order for the sum to equal 1000. Now clearly we're not going to get exactly 1000 because we're requiring the least number of terms required for the sum to exceed 1000. So if we get a decimal for n, we need to round that up to the next whole number. So if we rearrange this, we obtain 3 to the power n equals 1001. And then let's now solve for n. So we take logs, as shown here, and this gives us that n equals log 1001 divided by log 3. This is equal to 6.29. Now, as we said earlier, we're required to find the least number of terms required for the sum to exceed 1000. When n equals 6.29, we have that the sum equals 1000. Clearly this isn't possible because we're looking for whole numbers. Therefore, the least number of terms is 7. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solution. So in this example, we're required to find the sum of the geometric series shown on your screen. So let's solve this. Let's rewrite this series out again as shown here. We have the first term A is equal to 62,500 and the common ratio R is equal to minus 12,500 divided by 62,500. In other words, the second term divided by the first term. This gives us that R is equal to minus 1 over 5. We also know that the nth term is 4. And therefore, if we plug in all these values into the formula for the nth term, we obtain 4, which is the nth term, equals 62,500, the value of A, times minus 1 over 5, which is the value of R, raised to the power n minus 1. And of course n is the value which we're looking for. Multiplying through by minus 5 to the power n minus 1 gives us this expression here. And of course notice that 62,500 is positive, so therefore the minus in the brackets on the left hand side is redundant. And we can actually say that 4 times minus 5 to the power n minus 1 equals 4 times 5 to the power n minus 1. And then we've divided by 4 to give us this expression here. Giving us this value for n minus 1, which is equal to 6. So we have that n minus 1 equals 6. And therefore the value of n is 7. Now that we have established that n is equal to 7, we can now find the sum of the geometric series. So we substitute all these values into the formula for s subscript n. So we plug in A here, the value of R here and here, and the value of n here. And this gives us that s subscript 7 is equal to 52,084. This brings us to the end of this session. If you have understood its contents, you should be able to prove the formula for the sum of a finite geometric series and apply it. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.